Hello and welcome to another tutorial. In this tutorial, I'm going to continue our discussion on root finding algorithms and bisection method. So this is the first method that we're going to discuss, and we said that bisection method doesn't really work for the cases where the function is actually tangent to the horizontal line and it doesn't cross the horizontal line. And the problem with that is that in the bisection method, we try to bracket the root, which means we try to start with an interval around the root and look at the basically the sign of the function at the beginning and the end, and try to reduce the size of the function until we get very close to function. And it all is based on the sign of the function. So if the function doesn't crosses the horizontal axis, it doesn't change sign, and our bisection method actually fails. Alright, so fast and effective for simple or odd roots, because in these cases the function actually crosses and changes sign. And its order, it's a binary search, or the order is the log. So it's not linear or exponential, it's a log, so the growth is log. And it's based on a binary search, and I'll explain what it is. And it's the simplest method based on our general lemma, which says that if f of a times f of b is negative, we are guaranteed to have at least one root. And it does not work for roots with even multiplicity, where the behavior of the function is tangent on the horizontal axis. All right. Now, how does it work? So with the root bracketing, we start with an interval that we know that the function has at least one root, and based on that is based on f of a times f of b is less than or equal to 0. Now, as I mentioned before, equality here is not necessary, because it's trivial that we should check for a and b first to make sure that whether or not they are the actual roots. So it's very easy and trivial. So we can assume that they are not the roots, because if they were, we assume that we have already tested them and we have found them. But let's, for the sake of argument, let's have the equality here. All right. And so if f of a times f of b is negative, which means that, okay, our continuous function has in fact a root. And the way the bisection method says that, okay, now divide the interval in half. So look at the c0, which is the midpoint, a plus b over 2. And start the same. Now look at the interval a c0 and c0b. All right. If f of a times f c0 is less than 0, we know that the root, if we have only one root, it should be here. We could have more than one root, and the other root could be in the other half interval. Or at least we know that if f of a times f c0 is negative, we are guaranteed that we have one root in this interval. Okay. Then we again find the midpoint here, c1, which is a plus c0 over 2, and then test the f of a times f c1, and then f c1 times f c0, and then also for the other interval. So one path is like this way, we divide in half and continue. Or if f of a times f c0 is not 0, it's actually positive, then and fb times f c0 is negative, then it means that the root is actually in this half of the interval, in the second half. And then we find the midpoint c1, which is b plus c0 over 2, and then test for the other two halves, c0 c1 and c1b. All right. Now the beauty here is that we can do it recursively. We can employ a recursion. We start with an interval and we try to recursively go down the tree to find the solution. And when do we stop? If you recall, when we discussed the recursion for the sequences, we said that we should have initial conditions, or the stop condition for the search. And the initial condition is that when the interval that we end up with, like the length of the interval is less than the error, that we want, then we can call any point in that interval an approximation of the solution. And the typical thing to do is take the midpoint, the middle of that interval, as the final approximation. Now, what if we search and we don't find any roots? Let's say initially we don't know, we just arbitrarily pick A and B, and we don't know whether f(a) times fb is negative or not. So we can do two things. One, we can return null, which is not recommended. If you recall, at some point I discussed this. Or we can return nan, and nan in the double class. For the wrapper double.nan, if you recall, we can use the nan from the double class, which is not a number. And the reason that I don't recommend returning null, because during the runtime you could actually end up with an exception, null pointer exception, which is not good because it can actually break your program. But if you end up with nan, it's not an exception, so it doesn't break your program. Alright, so the idea here is that we do recursion by doing this binary search. And then regarding the error, we can define an absolute error. And the absolute error is basically the fact that the length of the interval is the absolute error, right? Is the maximum error that we can have, because we can select any point here, because we know that we have a root in this interval. And the worst case is that the root is very close to A, and we pick a point very close to B as an approximation, right? So as we divide the interval in half, the error is actually also divided by half. The error is reduced. So how many steps do we need? How many times do we need to break? So that depends on our error. What is the error that we want? So again, just like the sequences, we don't know the exact value of the solution, so we don't have the exact approximation of the error, but we can define a sequence of errors. So this is actually a sequence of errors, similar to the way we define the sequence for the limit of a sequence. Relative error is the new approximation minus the old approximation divided by the old approximation, or the new approximation. Now if we start with the initial error, epsilon 0, which is b minus a, that's the initial maximum or the worst case error. And then after n division, we end up with b minus a over 2 to the nth power. That's the error for the nth step. And therefore, if we set the epsilon n to some error epsilon that we want, the number of steps is log 2 of b minus a divided by the epsilon. All right? Now the problem here is that, and the reason that we have other methods to enhance bisection is that sometimes the root could actually be very close to one of the A or B. It doesn't have to be right in the center or close to the center. If it's close to one of the edges or beginning or end, then doing the bisection just adds extra cost to the search, right? Because instead of dividing by 2, if we divide by 3, then we can get faster to the root. So division by 3, 4, 5 could be enhancements to the bisection method, right? And the other thing is that we can actually set an initial guess for the root. That could in fact help with the speed of convergence. Another thing that is interesting is that here, as you can see, the number of steps for a given error that we want, the number of steps depends on the actual length of the interval, right? Which is not good. So if the initial interval is large, then we have to go more and more steps. But one trick that we can do is that we can easily find a linear map that maps the value of a and b to the interval 0 and 1. It's very easy to find the function, right? And once we do that, we can also use that map to scale the function. So we find the root of the scaled function in 0 and 1, and then we scale it back. The good thing here is that the length of the function is 1. So the number of steps that we need to search in order to get the error that we want is always fixed. It doesn't change with the length of the interval, and that's a very good thing to have. All right. So you map the interval to 0 and 1, you scale the function also, and then you search for 0 and 1. Once you find the root here, you map it back to the interval a and b, to the original interval. So the way we're going to implement this in Java is we're going to implement a binary search using recursion. And step 1 is to, obviously we're looking for we have a real function, so we define a functional interface. That gives freedom and flexibility. And then actually I had it down there. So we're going to define an interface for our real function, and it's going to only have one method that has the value of the function, so it's a functional interface. And then define a class for implementing the root finding algorithms. One of the methods is bisection, and the bisection basically takes the initial value for the interval, basically takes 2 points a and b and tries to implement the bisection. And we're looking only for one root, obviously, because bisection can only guarantee one root. And then we can also make it more advanced by having an initial guess for the root. And then we have to also define the stop criteria. All right, so let's head to Eclipse and try to implement the root finding. So I'm going to create a new Java project. I'm going to call it demo roots. All right, and here the first thing I'm going to create in the source folder is an interface. I call it real root function. So this is a function that is going inside the real root object. All right, it's not necessary, but I'm going to annotate it as a functional interface. So at runtime, it's going to double check whether or not it has only one abstract method, double value, double x. So it should have only one abstract method. So if I add another method, for example, double function, it's going to complain because it says that the annotation is functional interface. And now you have two abstract methods, so it's not a functional interface. And the beauty of the functional interface is that we can use it as lambda expression. Which is helpful when you have a expression for the function. So this is our interface, and it's always recommended to program to interfaces, especially functional interfaces. So we're going to have a class called real root. All right. In this real root, what I'm going to have is a real root function. I call it func, and then I'm going to have a constructor real root, and here I'm just going to pass the function real root function func. And then because the name of the local variable is exactly the same, we have to use the this pointer, this.func equals func, otherwise we're shadowing the global variable in the object. All right, so the first method is bisection method. So public double bisection, and as I mentioned, we get double start, double end. So this is the start and end of the interval. So what are we going to do? So obviously, if there is no root, we're going to return none. So let's start with a double root equals double dot none. All right, and then return root. So we're going to get the root, and then if other lines that we put here fail, then we just return the none. Then we're going to check for start and end points, because if you recall, I mentioned it's very easy to check for that. So if check for, and then the stop criteria, stop condition. If math.abs of func.value at start is less than the error, so we're going to define two errors: absolute error, that's 1e negative 10, and then double relative error 1e minus 15, for example. If func value at the start point is less than absolute error, all right, then what we can say is that, okay, the start point is a root, right? So return start. Else, if basically the same thing for the end point, less than absolute error, return end. All right, else if, so we have two stop condition, and then the last one is the interval is very small, so the length of the interval is actually less than the error. So if math.abs end minus start divided by end, okay, is less than real error, or let's also define it with the start. Then we're going to call it we're going to do a print stopped, and then we're going to return any point. So in order to do that, we define a variable guess, which is the midpoint of the interval, the start plus end, and we just return guess. So at the some step during the recursion, if our guess or the midpoint satisfies, if the interval satisfies basically the relative error, then we just stop and call the midpoint of the interval an approximation. So at each step we check for the beginning of the interval, end of the interval using the absolute error, and then we use the relative error. We could also just check for the absolute error, but here I'm just writing the actually we can add it as an or. Else math.abs end minus start is less than abs error, or math.abs, yeah, that's it. So we check for two relative errors, and the reason I'm checking for two relative errors is that either start or end could be 0. So if end is 0, this division returns infinity, which is not good. Then we can check for this one, right? So these are all the stop criteria. And what is the actual search? The actual binary search. We're saying that, okay, if so we take the midpoint and test it with the start and end. So if basically func.value at start times func.value at guess is less than or equal to 0, I'm including the equality. Then I'm going to first print that I'm going to the first partition or first half. Alright, and then I'm going to return, so basically I'm not going to return, I'm going to return call the bisection and tell it to go inside the start and guess interval. Alright, and then obviously we have an else if func value at guess times func value at end is less than 0. We're going to do a sysout of second half, and then we're going to call the bisection on the second half, so guess and end. All right, so if this fails, if this works, then we go inside. If it fails, it goes inside. If this fails, both of them fails, then we just return none. We say that, okay, the bisection method failed. All right, and what the other thing I'm going to do, I'm going to do a sysout on the absolute error at each step, end minus start, and then also do a do one on the relative error. And we can have two cases, so let's use this one for example. All right, let's go and test it. So here I'm going to create another class, the test bisection, and I want to have a main method here. And in the main method, what I'm going to do first, I'm going to create my function. So step one, define function, and I'm going to use a lambda expression. I'm using lambda expression, so my function is going to be f of x is x squared minus 2. So I'm going to define a real root function, f or func 0 for example, equals actually let's do this, public static test1. Yeah, I'm going to move these two, and then here I invoke test1. So here I'm going to say that x goes to x times x minus 2 using lambda, and then I define a, and it's a void function, it's a void method, and then I define a real root, and then I pass in the function. Obviously I need to use the new. All right, so far so good. And then we're going to just do system.out. Or we can say that double root or result is root dot bisection start and end. For the start I'm going to go from 0, for the end I'm going to go from 5. And then system.out.println result. All right, so let's see what happens. So our absolute error is first 5, right? 5 minus 0, that's the first interval. The relative error is infinity because we defined the relative error here with the start point, and here it's 0, so it returns infinity. And then we go into the first half, so 2.5, it says that 0 and 2.5, the value of the function changes sign, so it goes into the first half, goes into 0 and 2.5. So absolute error is 2.5. The relative error is still infinity because the start is 0, but then it goes into the second half. 0 to 2.5, it's 1.25 and 2.5, so it goes into the 1.25 and 2.5, and then goes there second half, first half, and eventually the absolute error becomes 9.3, 10 to the negative 9. The relative error is 6.58, e to the negative 9. Now obviously here the loop terminates because of the absolute error. So if we increase this, let's say we also set it to -15, we end up with the absolute error of 1.11 10 to the negative 15, and the relative error is 7.8 10 to the negative 16. And the root that we find is 1.4142, which is very close to the square root of 2. So let's do a sysout math dot square root of 2. 1.4142135623733095. So it's basically the exact value, right? And let's make this -5 to 5. Quite surprisingly, this one fails because at -5 and 5, both the value of the function is positive. So the bisection doesn't guarantee any root, and it doesn't know where to go, so it fails. Actually, it didn't fail. It okay, it's so that's okay. That's because we're not comparing -5 to 5. We're not comparing the sign of the function here. We're comparing basically the start with the midpoint, and here the midpoint is 0, and the function actually changes sign at 0. It becomes negative. That's why it still works, and it converges to, and again, because we look into the first half of the interval first, it looks into the -5 to 0 and finds the negative root, -1.4142. okay, and then if I change 5 to -5, so again it looks into the 5 and 0 first, so it should find the positive root. Yes, I mean, obviously this way of doing things is not recommended, but for now it works. And let's say we do -5 -2, for example. This should fail, so it returns a NaN because all the conditions, all the stop, and all these two tests, which are the basic of the binary search, fail. So eventually it returns a NaN. And that's a good thing, because then we can check whether or not we have the bisection failed or not. We're not throwing an exception, or we're not returning null. We're just saying it's not, it's NaN. And it's much easier to handle NaN than, for example, an exception or a null. So if I say 2 divided by result is NaN, the result is also NaN. So it doesn't throw exception, it doesn't throw error, it just returns a NaN again. Okay, this was the idea of the bisection method and the binary search. We can, let's say, for example, the function is tangent to the horizontal axis, x minus 2 times x minus 2. And I look for 0 and 3, for example. It fails because the function doesn't change sign. So none of these tests work actually. None of these tests results in a recursion. But if we have an odd root, so we have x minus 2 3 times, then yeah, it converges to 2 with a relative error of 10 to the negative 5. And yes, so this was the idea behind the bisection. In the next videos, we're going to look into other methods, the methods that are more advanced than just a binary search. Thank you for watching, and I'll see you in the next video.